So, good evening, everyone. Welcome to the Week 11 live session for the NPTEL course Computational Mathematics with SageMath. I'm Anish, a PhD candidate in aerospace engineering at Bangalore. As is the process each week, we'll be going through a set of problems which will further elucidate the concepts that have been taught in that particular week's lectures. So, we have a few examples. Example number one, convert the following LDP linear programming problem into standard form. So, we have been given an objective function which is z equaling 9x1 plus 8x2, which we have to minimize, subject to few constraints, x1 minus 2x2 being greater than 3, 3x1 minus 4x2 being less or equal to 5, and 6x1 minus 7x2 equaling 8. Here x belongs to the real line, whereas x2 is strictly non-negative. So a standard, as we have learned in the class, a standard linear programming problem is of the form f of x is equal to c transpose x, which is the objective function to be minimized, subjected to ax equal to b and x greater or equal to 0. So with a few conditions, c and b belonging to Rn and Rm respectively, x A being an m cross n matrix with m less or equal to n. With A as a standard linear programming problem. So like we have learned, this has the form of an objective function f of x is equal to c transpose x to be minimized, subject to the condition ax equaling d and x greater or equal to 0. So here we note that C, B and X belong to Rn and Rm according to their dimensions, and A is an m plus n matrix with a full rank. So with m less or equal to n, and the inequality x greater or equal to 0 basically restricts x to lie in the positive quadrant of the corresponding space, higher dimensional space. Right. So with this in mind, we'll be going through a few steps. Firstly, we have been given that x1 belongs to the real line. So to satisfy this constraint, we'll be replacing x1 with variables y1 minus y2. So, and y1 and y2 will be restricted to the non-negative side of R. Next, x2 will be replaced by the variable y3. To convert this thing into, to convert these two inequalities into equality constraints, we'll be adding the surplus variable y4 and slack variable y5 to the first and second constraints respectively, which will transform the equations into, this should be y5. This will transform the equations into two equations which are given above. Next, I'll be rewriting this whole equation in the standard form. So the standard form basically means minimizing z equaling 9y1 minus 9y2 plus 8y3, same as 9x1 plus 8x2, subjected to these three equality constraints, y1 minus y2 minus 2y3 minus y4, obtained by substituting x1 and x2 as well as the surplus variable, and similarly 3y1 minus 3y2 minus 4y3 plus y5 equaling 5, obtained by substituting the slack variable y5, and the third equality directly substituting y1 minus y2 and y3 for x1 x2 respectively. And then we have y1 to y5 lying in the positive quadrant of 5-dimensional space, so to speak. So this converts our problem into a function C transpose x as our C transpose x or C transpose y as our objective function, and ay is equal to b as my constraints. Okay, so standard form. Any doubts here? Okay, if not, we'll move to the next problem. We have been asked to formulate a few problems which are famously known. First is the job scheduling problem. So the statement of this problem reads that given an array of jobs where every job has a deadline and an associated profit if the job is finished before the deadline, it is also required that every job takes a single unit of time so that the minimum possible deadline for any job is 1. Maximize the total profit if only one job can be scheduled at a time. Normally, sorry, normally the job scheduling or job sequencing problem, we it's actually an integer, like the job sequencing problem. If you read about it, it's actually an integer linear programming problem, which means that no only integer solutions for the job deadlines are possible, job times are possible rather, and that is how we want it to be done. But if I open it up to the real space, how that would look like is, suppose we have 3 jobs with deadlines as that with the following deadlines and profits. Job 1 having a deadline of 4 units of time, say like 4 minutes, and profit of say $20 if it is if it's completed in up to 4 minutes of time. Job 2 takes say like 1 minute and $10 as the profit if completed before that deadline, and job 3 requires has a deadline of 2 minutes and yields a profit of $30 if completed within that deadline. So then we can define our linear programming problem as, let T refer to the total number of time available for the jobs. Suppose like you have 1 hour, so T would be like 60 minutes, and T refer to the total profits. Then we want to maximize the profits P, which equals 20J1 plus 10J2 plus 30J3, where J1, J2, J3 are the amount of jobs of job 1, job 2, and job 3 run respectively, and it is subjected to the constraint 4J1 plus J2 plus 2J3 is equal to T, and with J1, J2, J3 all being non-negative. So each job has some amount of time associated with it and is carried out in positive integer number of times, or rather non-negative integer number of times, where J1, J2, J3 are basically my non-negative integers. So this is the time constraint we have, and this is the profit that we have. So that is how a very simple form of the job scheduling problem could be written down as. Okay. It could be further complicated based on, so like one of the important assumptions here is that all the jobs are being run sequentially and they are independent of each other. But if in a more complex scenario, you could have jobs dependent on certain sub jobs and some sort of parallelization possible within the jobs that would lead to a much complex graph of connections of how jobs flow throughout. So this is a very simple example, but I hope this captures the spirit of the problem that we are looking at. Next is a slightly more involved problem. Again, another famous problem, the traveling salesman problem. Herein, we are given a list of cities and distances between each pair of cities. Then we are asked to find what is the shortest possible route such that one visits each city exactly once and returns to the origin of that city, returns back to the origin city. So one has to complete a loop. Say like if there are 4 cities A, B, C, D, then one wishes to go through all the 4, and then if the starting point is A, one wants to return back to city A itself. So how do we write this mathematically? Suppose as we first define decision variable xij, which is either 0 or 1, where xij is 1, and only if the salesman travels from city I to city j. Then our objective function is we wish to minimize summation I going from 1 to a, j going from 1 to a, cij xij. So what this whole summation would do is, if there is a if so you can think of Xij to be a sort of a matrix wherein each row has only one entry as 1 and all other rows are 0. So that is in a that could be in one way to think about a matrix formed out of Xij. And then our objective function is basically Cij into Xij. So term-wise multiplication of say the C matrix with X matrix, and we wish that that term-wise multiplication added together would give us our objective, which is basically the total distance covered from any possible route that we have chosen. Once this is done, we get the overall distance and then we will be trying to minimize it. Our constraints are, since we wish to visit each city once, xij for j going from 1 to n, summation of xij for j going from 1 to n is 1, which is exactly what I mentioned in the mentioned above, that you can think of uh, x xij in matrix form as basically having n number of rows, and in those n number of rows, like the n column entries, right? N minus one of them, n minus one of those are 0 and only one of them is 1. So that is the constraint. And then the salesman should return to the origin city, which means that on the rightmost column there should be again a 1 at the end. So that summation xin equal to 1. So, and salesman cannot visit the same city twice, which is basically the xii or the diagonal term being set to 0. So diagonal, once it is in city I, it the salesman has to move to city j, where j is distant from I. So an example of the following could be thought of as follows. Suppose there are 4 cities A, B, C, D, and the distances between those are given below. So these are the distances. So A to B is say 10, A to C is 20, A to D is 30, B to C is 15, and so on and so forth. You can notice also that all the diagonal terms will be automatically 0, as well as the distances will be, because it's a distance matrix, this overall distance matrix is symmetric as well as non-negative. All the terms are non-negative. Now, this is this basically is an linear programming integer linear problem rather, wherein if we want to minimize this Cij xij, so that would create minimizing 10 times xab plus 20 times xac plus 30 times x ad should be somewhere xda, right? So this whole thing, sorry, this should be 30xd, 30xd plus 10 times x ab plus xba plus 15 times xbc and so on and so forth. So this will create a large, some of the entries are wrong here. I'll change those, but I think in the optimization function, some of the entries 10, 20, 30, then 20, 10, and 15. It should be 10, 10, 15, 25, 25, and then 20, 15, 10, 20, 15, 10, and 30, 25, 10. Okay. So now it's fixed. So this is my overall objective function, which I wish to, which tells me about the possible, which tells me about distance for a possible route. And this is what I wish to set to 0. And then my constraints, if I think about it, are basically xa, x, XAB plus XAC plus XAD equal to 1. So from A you have to go to either B or C or D. From B you have to go to either A, C or D, and so on and so forth. So all four constraints are written down. And yeah, so this is like the route going from A, from B, from C, and from D respectively. I think I made a mistake here with this series of equations. I was trying to showcase non like no return to the same city in the root, but with this sort of equation, XAB plus XB equal to 1, it might also remove the possibility of XAB being non-zero, or rather XAB equal to 1. So I think I made a mistake here with this series of equations. Okay. So this is how, yeah. So this is how my formulation looks like, and this would be one way to say write mathematically what the traveling salesman problem looks like. We could there could be other ways to write this down, but yeah, like using the C matrix and using the distance matrix and the decision matrix along with the constraints, I could find my integer programming problem here. So yeah, uh, okay. Any doubts with this one or the previous one? Okay, if not, we'll move to the third problem. So we have been asked to solve an NPT using graphical method. The constraint, the objective is to minimize 13x1 plus 4x2 subject to three inequalities given here: x1 plus x2 less or equal to 8, 6x1 minus x2 greater or equal to 6, and 2x1 minus x2 less than or equal to 1 with x1 to both being positive. So we'll be first plotting the feasible region. So variables x comma y, we specify them as is a good practice. Next we'll be using a region plot where x plus y is less or equal to 8, 6x minus y is greater or equal to 6, and 2x minus y is less or equal to x and y vary from 0 to 10. And if I show the region, so this is how the region looks like. It's a triangle with all the three borders. The borders are shown below. Okay, we'll dissect all the borders together. So the first border is red, x plus y is equal to 8. This is the first constraint written in equality form. So like it's extended all the way till it becomes tight. The second constraint is 6xy minus 6xy minus 6x minus y greater or equal to 6. So that is tightened to 6x minus y equal to 6. So into an equality in the green color. And the third inequality is tightened to 2x minus y equaling 1 into this blue line. So this creates my region. Next, I wish to plot my objective function as a contour plot. And right, so the contour, we are plotting a contour for the objective function which is 13x plus 4y in the same space, xy going in the same domain, xy going from 0 to 10 with labels. So you can see this contour, from this contour plot, we expect that this point of this point on the triangle, rightmost point, somewhere between 2 and 4, seems to be the point where our objective function is being maximized, and it will should have a value between say 54 to 66. Right. So we'll be solving for the corner points. So firstly we'll be solving for x plus y is equal to 8. This is this line, and 6x minus y equaling 6 seems to be this line. So if I solve this true, I'll be getting a x comma y solution, and at that x comma y solution, I'll be plotting 13a plus 13 into x plus 4y. Same thing I'll do for the other two pairs of line, and together I get value of objective function at all the points, all the corner points rather. So 2 comma 6, 3 comma 5, and 5 by 4 comma 3 by 2 are my corner points, and the value of the objective function at these 3 points is 50, 59, and 89 by 4, which basically means that this point 3 comma 5 is my point which maximizes the objective function with the value of 59. So this solves this particular LPP using graphical method. Simple, straightforward geometric intuition to find the constraint region, following which contour plots to estimate, to get a feel of how the objective function varies over the region, and then solving for the corner points to obtain our final solution. Okay, we have already seen this like in using the simplex method, how if once we have this convex set coming out, our solution would lie on like the edges of this, either on the vertices or edges of this simplex of this region, provided that this region is indeed bounded as it is in this case. So, and in this case, we see that the region is bounded and the solution comes at a corner point. Any doubts with this problem? If not, we'll move to the next one. Here we are here we are again, like similar to the previous example, we have been asked to plot uh, constraint LPP with the constraints 2x1 plus x2 less or equal to 2, 2x1 minus x2 less or equal to minus 2, 2x1 plus x2 greater or equal to minus 2, and 2x1 minus 2x2 greater or equal to minus 2 with x1 x2 greater or equal to 0. So we already see from the problem statement that it seems like this identity, sorry, this inequality is sort of redundant, because x1 x2 being positive will make this whole thing greater than 0. So this will put a bound, this will also put another bound, and okay, this should also put a bound. So we'll be plotting this, or we want to find an optimal solution where x1 x2 are bounded to be positive, to be non-negative, and two different objective functions are provided. First, we'll plot the feasible region with these following constraints. So, as is a good idea, we specify the variables as x comma y, plot a region plot using all, by specifying all our constraints one after another, and bounding x and y to be on the non-negative side, which is what our constraints here say. So if I run this, I get this as my plot. So it seems to be a triangle of sorts, with two of its right-handed triangle with its height and base lying along x and y axis respectively. Next, we'll be plotting all our borders to express y equaling to 2x minus y equaling to, and so on and so forth in all the in four different colors. So there is so once we look at this, we see that uh, there is some constraint, specifically the blue constraint, which is 2x plus y equaling minus 2, which is not plotted within these specified lines. So which is not plotted rather within the specified domain x between 0 and 5 and y also being between 0 and 5. If I now plot a contour plot for my objective function, which is x plus y, again in the same ranges of x and y, I see contour plot to be like this. So it seems from an eye test, it seems like the topmost vertex x is equal to 0, y is equal to 2 is likely to have the maximum value of the objective function. So, okay. Next, with this in mind, we'll just calculate our two corner points and try to evaluate what happens at these 2 points. So, as we have seen, the corner points come at the intersection of, here it seems like they come at the intersection of red and yellow and red and green lines respectively. So if I only look up those constraints, red and yellow and red and green, and try to find out the intersection points and then calculate the value of objective function, I see that uh, x is equal to 0, y is equal to 2, which is this top corner point, has the maximum value of objective function equaling to. Suppose for whatever case, this inequality of the red line, which is 2x plus y is equal to 2, is inverted the other way. So 2x plus y is greater or equal to 2. That will create a large unbounded region like this. And if I now plot the contour plot for this region, I see that this has basically become an unbounded problem. So if I can let it be much larger, the contour will be, the value of the objective function for the contour plot will be much larger. So I have to also change it here. It's 10 by 10, it's 5, 5. Right, so in this case, this the contour lines won't end at all. If I'll just revert back to my original size, 6, my original region. So this is how it looks like. Okay. If I now look at the other objective function, which is x1 plus tan x2, here we'll write it as x plus tan y, and again plot the contour along with the region. This is how I see it. Again, I expect the contour to be maximum here at the top corner point, and again it is the intersection of red and yellow and red and green bounded lines. So if I run for those, the solution is 0, 20. The optimal point is 0, 2 with the objective function value as 20. Okay. Uh, One more thing we could say play around with is, suppose if you do not have any bounds on x1 and x2. then you can see that the bounded region basically becomes uh, like a diamond, and I'll just run the thing for other points as well. X1 and X2 are unbounded. So the borders look like, so you can see a nice clean diamond. And if I now plot the contour plot, right? So again, we expect this to be the point at, sorry, the top point to be the solution, and the top point, as you can see, is the intersection between red and yellow lines. So it's unchanged from the previous constraint solution, but now we will have to solve for, say, all the intersection points of the lines. All right. So there are not 6 points, there are only 4 points. And it's basically two sets of parallel lines. So uh, green doesn't intersect with yellow and blue doesn't intersect with red. So you only have 6 points. If I look at those 4 points resulting out of it, this is what I see. Okay. Right. So my objective function is maximized at x is equal to 0, y is equal to 2, even in the unbounded case. If I do this for the other objective function as well, this is how the plot looks like. Again, it seems like the top corner point is the one that we want. If I just solve for the 4 points, I think I'm repeating this line. Where is it? Yeah, I was repeating this line. Okay, again, the objective function, even in the unbounded case, is maximized at the top point of the diamond. So this is basically our solution for both the objective functions in both the bounded as well as the unbounded case. Any doubts with this problem? The next problem. So we have been asked to find all the feasible basic solutions for the problem given below, which is x1 plus x2 plus x3 equaling 1, 2x1 plus 3x2 equaling 1, and x1, x2, x3 all being non-negative. So we can think of this problem as ax is equal to b, where x is restricted to be non-negative. If I write down A and B matrices respectively, they are 1, 1, 1, 2, 3, 0, and B is 1, comma 1. Okay, so feasible solution, right? So matrix A will have matrix A is of the dimension m cross m rows, n columns, so 2 rows, 3 columns, and rank of A we assume it to be m. Basically, here we require the rank of A to be 2, and then we'll be taking the first m columns of A and writing that as, say, the matrix AB, and then AB into XB equaling 1, so that XB comma 0 becomes my basic solution. Okay, so we basically solve only for like a selected submatrix of A, get the solution, and uh, set the solution of remaining dimensions to be 0. This is XB comma 0. That creates a feasible basic solution. So feasible solution is any solution x which satisfies ax is equal to b, x greater or equal to 0, which is our NPTEL. And basic solution is uh, reducing going from A matrix M cross N to AB matrix, which is M cross M matrix. Again, AB also has a rank M. Create a solution XB is equal to AB inverse into B, and then that basically use that to fill, use that to write a matrix, write a vector X with remaining entries as 0, remaining N minus M entries as 0. So we can choose any pair of the three columns of A that we have here, and you can see that the first and second column, second and third column, as well as the first and third column, all three pairs are linearly independent. Before we proceed, rank of A is 2, just to check this valid. This is our basic assumption here. If I choose my first two columns as column 1 and column 2 respectively, then I can write my A12 matrix, submatrix as 1, 1 and 2, 3, and from which I will calculate my possible solution x12 as inverse of A12 into B. So that creates x12. Just to be sure that everything is alright, I'll be printing A12 into x12 and checking if that indeed equals my B vector. So this is my A12 submatrix. X12 is calculated to be 2 comma minus 1, and A12 into x12 is indeed equal to B. So we get true as the output here. To calculate my basic solution from the first and second column vectors, I'll name it as xp12, and it will have the first two entries from x12, and the third entry corresponding to column 3 is set to 0, which is basically what we have here. And from this, I am now printing A into my xb12, which is the basic feasible solution using first two columns. I'm multiplying that with A and checking if it is indeed equaling B. So my basic solution. So this is what my solution looks like. However, here we run into a problem. This is a minus 1. We require x to be greater or equal to 0. So actually, this turns out this is not at all a feasible solution. So it's automatically not a basic feasible solution. If I use columns 2 and 3, my submatrix becomes A23, from which I calculate x23 as A23 whole inverse into B. So this is my A23 matrix. This is my x23 vector. You can see that if I multiply this vector with this matrix, I get B, which is indeed 1 comma 1. Now same process, except we need to remember that this x23 corresponds to second and third column respectively. So the first column entry for the basic solution needs to be set to 0. So 0 and then x23. And I'm just for safety checking if A into this xp23 is equaling B. So this is how. So this is all the entries here. So all the entries here are non-negative, and this indeed looks like a feasible as well as a basic solution. Same thing I do with first and third columns. Create matrix A13, calculate x13 as my vector, and from that obtain my basic feasible solution, half to 0 half. So again, just to check x is positive, non-negative, making this a basic feasible solution. All these steps, we have already seen how to do this in class, but just I wanted to show the steps out once separately, lay them out separately. Okay, and so now we have matrix. Just we'll do it now in the way we have already done it in the class. I have my matrix A, I have my vector B, I augment them and reduce the augmented matrix to its row reduced echelon form. So matrix A, vector B, augmented matrix, row reduced echelon form. Right, so from this we can say that my original set of equations as well as my original set of equations as x1 plus x2 plus x3 equaling 1 to x1 plus 3x2 equaling 1, and they can now be written in their a new set of equations coming from the row reduced echelon form. Okay, and before we go there, we first get our x1, x2, x3 coming from our symbolic ring variables. So by with four such variables, so those four variables basically become x0, x1, x2, x3. Capital X is a subset of that. It's basically x1, x2, x3, and then I'll print, as I mentioned, my original equations as well as my uh, set of equations after row reduced echelon form. So x1, x2, x3, original set of equations are, as I mentioned, x1 plus x2 plus x3 equaling 1 to x1 plus 3x2 equaling 1, and set of equations of the row reduced echelon form, x1 plus 3x3 equaling 2, and x2 minus 2x equaling minus 1. So clearly, this system has infinitely many solutions. Three unknowns, two equations. To list all the basic feasible solutions, we'll be going through the same process we have seen in class. So, firstly, we we find out the number of columns as n, A as the list of all columns in matrix A, and basic solutions is initialized to an empty array. Next, initially basic solution is written down as an n-sized vector or n-sized array with all entries as 0. And for I ranging in all columns, j will go from basically I plus 1 to like the remaining columns of A. And from that we basically create a column matrix. So if we take say like the first and second column, we create a column matrix ai comma aj. If that matrix M is invertible, then we solve for the basic solution Bs of I and Bs of j equaling S0 and S1 respectively. So here we only have two equations, which is why I am directly taking the I and j columns. If we had more, we could have taken I, j, k columns and so on and so forth. And from those, we determine what my basic solution looks like. Only if the basic solution is non-negative, then we print it out. And before that step, we are appropriately assigning the basic solution I and j values uh, based on what I'm calculating from M inverse into B. So same as this AB inverse into B that we have here. Okay, if the basic solution, if it is indeed a basic solution and it's a feasible solution, then it is added to the basic solutions array. Otherwise, it is not added. So if I run this loop, as I mentioned, we'll be going through say column 1, column 2, column 1, column 3, and column 2, column 3 respectively. First solution is 2 minus 1, 0, which as we mentioned is not a feasible solution. Second is columns 1 and 3 give half half, and columns 2 and 3 give 0, 1/3, 2 by third. So there are two basic solutions that we have obtained from this sort of algorithm. So if you see, this is same with half, 0, half, and 0, 1/3, 2/3, which is what we have obtained here also. Okay, any doubts with this one? So the idea here with the above process was only to just show this algorithm in a bit detail in a step by step manner. Okay, if this is clear, we'll move to the next problem. Here again, we have been asked to find all basic solutions of Ax equaling B, where A is a 2 by 4 matrix, B is a 2 by 1 array, a vector, and X is non-negative. Now we'll not go through the entire process above, but only go through the algorithm that we arrived at end of example 5. So we'll first print A matrix, B vector, augmented A augmented B, and as well as its row reduced echelon form. So 2 6 2 1 6 4 4 6 augmented with 3 2, changed to row echelon form. This is how it looks like. Next, we obtain a sim set, sorry, an array of symbolic variables x1, x2, x3, x4 in the capital X variable, and we'll be printing both our original equation X is equal to B as well as my set of equations after row reduced echelon form. Right, so x1, x2, x3, x4 is my vector. Original set of equations is this, and set of equations after row reduced echelon form looks like this. So clearly we have four variables, four unknowns, but only two equations, making this to be a system having infinitely many solutions. Next, we'll be listing all the basic feasible solutions. Again, the same process. Rank of matrix A, I have not checked. I should print that here. Rank of matrix A is 2, so we'll be taking two columns at a time to create a 2 by 2 matrix. Here we have four columns. Choosing two out of those will basically create six possible submatrices, uh, six possible basic solutions. Then we'll check its feasibility, and if everything goes right, we should have up to six basic feasible solutions. Same algorithm as above. So if we take the first two columns, we get a basic solution of the form 0, half, 0, 0. We can quickly check it with 0, comma half as my vector and first two columns. So 2, 6, 6, 4 multiplied with 0 half will give me 3 and 2 respectively. So the uh, first two columns do indeed give us a basic feasible solution. Columns 1 and 3 do not give us a feasible solution. 1 and 4 also do not give us a feasible solution. 2 and 3 give us a feasible solution, which is same as column 1 and 2. So what is 2 and 3? So 2 and 3 is this 6214. Similar multiplied with 0 half. Sorry, multiplied with half 0 in this case, because the entry corresponding to second column will come earlier. So half 0 will give us 3 2. Similarly, if I have 6416 as my submatrix, which is second and fourth column, again half comma 0 will come as my solution, which tells me that columns 1 2, column 2 3, and column 2 4 all have the same basic solution 0 half 0 0, and this three possible combinations of submatrices do not have a feasible solution, which makes my number of basic feasible solutions to 1, and that being of the form 0 half 0 0. Okay, this hope this example is clear and it outside this one. We'll move to the next problem, example number 7. Again, we wish to find the basic feasible solution for the problem given here. X1, x2, x3 equaling 1, 3x1 plus 2x2 minus x4 equaling 6, and x being strictly non-negative. So again, we'll print out our matrix A as well as its rank, and then also print out our target vector B 1 1 and 3 2 0 minus 1, and then we'll be printing out A augmented B as well as A augmented B in the row reduced echelon form. So this is how my A augmented B matrix looks. A matrix looks like rank of A is 2. So everything's set here. Next we'll be looking at the augmented matrix and finally in its row reduced echelon form. Again, we'll be printing out both the original set of equations x1, x2, x3, x4 as my variable. These are my two original set of equations. These are my equations of the row reduced echelon form. Clearly, same thing, four variables, four unknowns, two equations, infinitive any solution. Again, the same look that you have done in the previous problem to find my basic feasible solutions by taking two columns at a time. So first and second column give us the solution as 4 minus 300. First and third column give us 2 minus 10, 20 minus 10. First and fourth, second, third, second, fourth, and third, fourth. So basically we go through all six pairs of columns, and then everywhere we find the solution xb equal to ab inverse into b. Unfortunately, xb is not non-negative in any of these cases, making this problem to have no basic solutions. We could potentially play around with the matrices and see what happens in that case. So suppose this is how one possible matrix could look like, and here we have changed this plus 1 to minus 2. Again, it's a rank 2 matrix, and once we solve this, we do, in this case we do see a few basic solutions, specifically two basic solutions for columns 1 2 and columns 2 3 respectively. Okay, I think same as the earlier problem, but uh, just wanted to show a case where you may not have, say, any solution at all, any basic feasible solution. Okay, with this, I think this should also be clear. Uh, if not, I'll wait a moment before moving to the next one. Okay, then example number 8, we want to use the simplex method, and wherein our objective is to maximize the objective function z is equal to 3x1 plus 2x2 plus x3 subjected to 5x1 minus 2x2 plus x3 less or equal to 6, 2x1 minus x2 minus x3 less or equal to 4, 9x1 minus 4x2 minus x greater or equal to 50, and x being my positive variables. So we'll be using the help of the interactive LPP problem, uh, which is an inbuilt function in Sage. So if I oh, interactive LPP problem, right? So what does this say? So it basically constructs a linear programming problem, and so only for educational purposes, this is what it's saying. So A is the matrix of constraint coefficients. B is a vector of constraint coefficient terms. So RHS of the constraint. C is a vector of objective coefficients. Right. And example is given here. So we'll be using this to write down our matrix A, which is 5 minus 2 1, 2 minus 1 minus 1, and 9 minus 4 minus 1, multiplied with x should be equaling or greater or equal to b. So you have 6 4 15 6, 4, and 15 as B, and the third constraint is a greater or equal to constraint. Our C is the coefficient vector for the objective function, so 3, 2, 1. And with this in mind, our all of the variables are greater or equal to 0. With this in mind, I'll be running the interactive LPP problem. I show P in its standard form. This is how it looks like. So you can see that it has inverted the coefficients as well as the right hand side of the B matrix for the third equation, for the third constraint equation to give me standard form. Now we'll be using the simplex method. So if I run the solution, so it tells me that the original problem is infeasible. Okay, then if I flip this around, then this problem becomes unbounded in the x2 direction. Okay. So how does the simplex method work? If you remember, like this printing also is showing you that you add a slack variable x4, x5, and x6 to all the three, to the left hand side of all the three constraint equations, and then move everything to the right hand side and write your objective function as in terms of your on the left hand side in the terms of your other type variables x1, x2, x3 respectively. And then what we do is we basically uh, what we do here is uh, so what we essentially do is we wish to play around with the slack variable and find out and first look at the direction, sorry, the coefficients in the objective function. So 3x1 plus 2x2 plus x3. 3 is the largest non-negative coefficient. So we'll first check x1 as the variable to be tightened, and then look at where x1 occurs in all the three functions. We see that it has the largest negative coefficient in x4. So we move it around to tighten this constraint by moving the slack variable to basically get to 0. And then the same process happens as we pivot through a series of all the corner points or the vertex points of the bounded region that is constructed using my constraint equations. So in this case, it does turn out that we do not have like a solution to the problem. Okay, we'll move to the next problem where we have again where we have an objective function z is equal to 70x1 plus 50x2 plus 35x3 subjected to three constraint equations. I write them down in the using the interactive LPP problem module with ABC constraints, and now write them down in the standard form. If I run the simplex method, so I think I should have put this example above that one, because in this I am able to you can see clearly what is happening. X4, X5, and X6 are the slack variables which are added to convert my equation into from an inequality into an equality, and then we move my variable, then we move around to obtain my slack variables on the left hand side and write down my objective function here. Then we determine, since x1 in z has the largest positive coefficient, we choose x1 as the variable to tighten, and we have to figure out from where do we exit this To do so, we'll look at which of the slack variables has x1 in the uh, smallest negative direction, so that is -2, and then we flip around x5 onto right hand side and x1 into left hand side to obtain an equation like this. That basically, this equation is now basically plugged into my objective function z. So 70x1 becomes 70 into 50 minus so on and so forth, right? So my objective function becomes 3500 minus 35x5 plus 15x2. As we have seen, because x5 is the slack variable being added here on the second equation, and this LPP is written in the standard form, we notice that x5 has to be follow the constraint of being non-negative, which is why we are not too worried when a negative coefficient comes here. This constant will automatically inform us about what value my my optimized equation takes. Sorry, my this constant will take care of the optimum value of my objective function. Next to figure out which vertex to pivot to, again we look at z. We see that 15x2, x2 is the kite variable on the right hand side, has the largest positive coefficient, and with this in mind we look at where x2 occurs, and we will be using that x2, we'll be using minus x2 occurring in x4, substituting it inside, sorry, flipping this x2 to the left hand side and x4 to the right hand side, and then substituting x2 is equal to 40 plus 2x5 minus x4 plus x3 into my objective function. Once we put this, we see that we see that my objective function is now changed again to 4100 minus 5x5 minus 15x4 plus 15x3. Again, x3 is the slack variable, sorry, x3 is the final variable that is remaining. We look through the equations, substitute x3 in, substitute x3 in the form of x1, and then we should be substituting x3 in the form of x6 here. Okay. Okay. Here in this case, they have chosen in the inbuilt function, they have chosen x3 to be substituted with x1, and once you do that, the objective function starts looking like this, right? So with this, what happens is basically my constant in the all the coefficients for x4, x5, and should be x6, all of them become basically negative, and because they are negative, and the constants, or the the variables x4, x5, x1 all have to be positive or non-negative. Any deviation to the variables from 0 would mean that my optimum, my z value no longer remains maximum. So which tells me that the optimum value of z is 4550 when x5 is 0, x4 is 0, and x1 is also 0. So if I substitute x5, x4, x1 to be 0 in this equation, I get x2 to be 70, x3 to be 30, and x6 is also 70. So my optimal solution becomes 0, 70, 30. Okay. Okay. Hopefully this demonstration is clear. So like in terms of programming, there's not a lot of steps that I have written here. Sage already takes care of all those. And we have also seen in class how we could write our own pivoting functions for columns and row, and then we use them. Hopefully with this demonstration, the idea of how simplex method works is clear, wherein we substitute, say, my type variables x1, x2, x3 with uh, my slack variables x4, x5, x6 respectively. Here in the last step, it's not happening with the inbuilt function, but what this essentially does is, because my slack variables all have to be non-negative, whatever coefficient of z arrives is my optimum function, and that is the optimum when all the slack variables are zero. So, which points to the fact that my optimum solution will always lie on one of the vertices, or, or an edge line corresponding to the enclosed region based on my constraints. There's a very interesting story to how this simplex method was done, and like I forgot the name, but like as far as I remember, the story goes like this: that a professor, I think this is 1938 or 13, and a professor wrote down a couple of problems on the blackboard, and a student arrived late in the class, in the maths class, thought that was homework assignment for that particular class, took them back home, took about a week to solve it, returned it to the professor along with an apology note for being late to submit his homework assignment. And little did the student know that this is actually a famous unsolved problem in mathematics. So that basically gave us the simplex method. I'm forgetting the gentleman's name at the moment. Anyways, okay. So I think we already arrived at the last problem for the day. So again, similar problem where we have to maximize an objective function subjected to three constraints given here in form of three inequalities, as well as the constraint of x being non-negative. I'll just specify my A, B, C matrices respectively and write down the LPP problem using the interactive LPP problem. I'll write down my interactive LPP problem, and once I have that, I'll just write it down in the standard form. So maximize 3x1 plus x2 plus 5x3 plus 4x4 with the constraints. Sorry. With the constraints 3x1 minus 3x2 plus 2x3 plus 8x4 being less or equal to 50, 4x1 plus 6x2 minus 4x3 minus 4x less or equal to 40, and as well as the third constraint. And now run the simplex method. So x1, x2, x3, x4 are my original variables, x5, x6, x7 are my corresponding slack variables to convert these inequalities into equalities. We look at the objective function, and ideally, so this is entering through x1, but ideally we'll be trying to maximize the objective function. To do so, we'll be looking at the coefficient of, looking at which of the coefficients from x1, x2, x3, x4 is the largest positive. So that would be x3. In this case, we are entering x1 and leaving x7. So basically rearrange the third equation, and after rearranging this form of x1 is being plugged into my z. Similarly, next we enter x2 and leave from x6. Finally, we enter x3 and leave from x5. So this is how the equation looks like. And you can see that here we have run into problem that this problem is unbounded in the x7 direction. So x6, x5 and x4 have to be minimized and can be set to 0. But x7 being non-negative can be greater or equal to 0. We basically say that z can keep on increasing after even a long time. So this will basically stop us from finding an optimal solution. If I were to say forcibly try to find a solution, I might have to add another constraint. Suppose I'll just simplify it 1, 2, 3, 4, and this is 100. Constraint type less or equal to. And if I now run now CP in its standard form, this is how it looks like. If I now run the simplex method, I end up having a solution, right? So x1, x1, x8, and x4 are all non-negative. So for z to be maximum, these all need to be set to 0. Once we do that, we see that x2, x3 become 5 and 30 respectively. This is how an optimal solution can be obtained. Okay, so uh, in here I basically wanted to show how an unbounded problem could look like, and with that in mind, how we can theoretically put a bound or like make it solvable. So this is one way of looking at it. Right. So I think I've covered a little early all the problems that I had for this week. Any doubts with say either the simplex method? Like I think it's a little tricky to understand at first, but once you get a hang of it, it's quite useful.